When I was a kid, there was this thing you would say to another kid when you greeted him. You'd say something like, Transformers, more than meets the eye. And so today we are going to talk about Transformers. And it's not that movie, but they're everywhere and they're taking over also. I will start by showing you that this is the battery charger for the very camera that you are seeing this video through. Whoa, this is kind of meta, right? This is, yeah, okay, cool. So it says right here, input 120 volts to 100 volts to 240 volts, huge range. It says 50 to 60 hertz, so something must be changing up and down. And the output is 4.2 volts DC, and it's 500 milliamps. So that's a very small current and a very small voltage output, but a much bigger voltage input. So something must be changing the voltage in here. So let's look at another one. I've got this one, where's one? Oh yeah, you might have a transformer for your laptop inside a block that looks like this. This one says that the input is, again, a huge range of voltage inputs and a range of voltage outputs between 22.5 to 18 volts. So the voltage is going down right here. It's called a step-down transformer when you do that. Got some other transformers here. Let's see, here's one. Yeah, here's a Radio Shack transformer, and it's got this plug at the end right here, and it was designed to power some small toy, probably. It says input 120 volts, 80 milliamps, and output 9 volts, 350 milliamps. Whoa! Okay, so I get more current out than I put in, and I get less voltage out than I put. And that's an interesting relationship. Maybe you're thinking about how those are related, but I want to see what's inside of this sucker. Inside of here, we've got we've got this thing, and this is a transformer. So we'll investigate how that works. We've also got some capacitors and some diodes, and we could talk about how all that goes together at a later time, but yeah, we don't need that anymore. And oh, here's a nice one from a Nintendo Entertainment System. You ever heard of those? They're kind of old. And it says input 120 volts and output 9 volts. All right, let's see what's inside of it. Oh, inside of here we've got only a transformer and a little resistor right there. That's how you power your Nintendo Entertainment System. I mean, it's how I used to power my Nintendo Entertainment System. Here's one that's already broken. Oh wow, now it's really broken. Yeah, and you've got a transformer right here and a capacitor right here and some diodes. That's all you need to go from AC to DC and to change your voltage. It says it's 120 volts and it goes to 12 volts, like a factor of 10. That's pretty cool in voltage. What about this guy right here? This is a lab transformer. Now I want you to start noticing what sort of things transformers have. If you're looking over here, this guy has, it looks like some kind of an iron core, but it's not just solid iron, it's a whole bunch of plates of iron, and we can talk about why that is. Actually, that's a little bit advanced, I'm not gonna talk about that. But lots and lots of different plates of iron all glued together. And this has, you'll see the same thing. If you look on the side view, you've got a whole bunch of plates of iron glued together, and I'm gonna unscrew this so you can peek inside of it. First of all, you notice that there's a top thing and there's another, I mean, these are all different plates of iron all stuck together. And then this and that are each coils, and they're not electrically interacting with each other. You got a coil here and a coil here. It tells me how many turns I have. I have 110 turns right there, and I have 200 turns right there. And the idea is you can hook up electrically to these guys, and this coil will interact with that coil by simply the magnetic flux that's going through this, because when this is connected here, you've got a magnetic loop. And so if you try to get a north pole here, you'll kind of get, well, not really a magnet, you'll just get like a loop magnet. And all of the magnetic flux is contained right inside of there. I guess I should assemble that later. Let's put it aside. Really, at its most basic, all a transformer requires is a coil and another coil that can talk to each other. Like the magnetic field from one coil interacts with the magnetic field of the other coil. So you could put them next to each other, but that's not perfect. What you really want is to have something that's ferrous going between them, something to conduct the magnetic field, guide the magnetic field to make sure it goes between them. And then you really want to loop this around so that the field is only connecting those two, so you guarantee the flux through one is equal to the flux through another. So I'll draw a schematic of that kind of a thing. Let's see, I'm gonna start by drawing the metal. Let's say that it's green metal. You've got this metal ring. It has to be ferrous metal, so it is magnetizable, but you don't want it to be a hard magnetic material. You want it to be a nice soft magnetic material so it easily magnetizes and easily demagnetizes. And this thing has got to be solid, or plates glued together, or something like that. Then, I'm going to come in here with a wire, and this wire is part of my primary circuit. Here I am coming in here with a wire that's going to go above and behind, and above and behind, and above and behind, above and behind. How many should we put over here? What do you want? I don't know. I can't hear you. And behind, and then we'll leave at that point. All right, so that's what I'm going to call the number of turns on the primary side, and we'll connect something over to the primary side soon. I'm going to put fewer turns over here on the secondary side. I'm going to come around here and just do, we're going to go behind, and then we'll go above and behind. We'll go above and behind, and then we'll leave. So this is the number of turns on the secondary side, and I'm not doing them in any particular ratio. It looks like I got a factor of 2 to 1. We got 6 over here and 3 over here. And this thing right here is called the core of the transformer, and that's our ferrous metal. So I'm gonna have some voltage over here. I'm gonna have a resistor, right? Which is probably my load. So that's our goal, is to deliver some power to the load in the transformer. So that might be your Nintendo Entertainment System or your laptop or something, and this would be the voltage input from the primary. But across the load, I'm going to be able to measure a voltage, and that voltage I would then call the voltage of the secondary. Voltage of the secondary, and over here I'm going to be actually providing a voltage. So this is the symbol for an AC voltage generator. The reason I have to use AC is because, well, if I want the flux to change in this core, that's easy. All I have to do is turn on even just a battery right here. And that would change the flux, which would cause a voltage over here. But gradually, you see, this loop would get used to the new flux, and then there wouldn't be any voltage over here. But what I need to do is I need to change the voltage through here continuously. Let's see, if I continuously change this voltage, then I'm going to get a flux first this way, and then that way, and then this way, and then that way, and this way, and that way, and this way, and that way. And similarly over here, because the flux of the whole loop will be going counterclockwise and clockwise and counterclockwise. It's flux sloshing back and forth instead of, it's really domains changing direction instead of electrons sloshing back and forth as are present in this circuit. So in the circuit, electrically, you've got electrons moving. Here, you've got magnetic domains shifting orientation. And as a result, inside here, this loop gets continually pissed off because you keep trying to change the flux through it and it doesn't like it. So it induces a voltage that gives you then a current through your load. So that's the idea. Now let's do some equations. I'm saying that the voltage of the primary, this is the voltage of the primary. I'm not going to call it the voltage of the source because then we could confuse it with the voltage on the secondary side. I'm going to use just primary and secondary. The primary voltage will be, well, I guess it's negative N primary. I have to label which number of turns I'm talking about, right? Times, it's just the change in flux in the primary circuit divided by time. And the voltage on the secondary side of the circuit will just be N times the, N secondary times the change in flux in the secondary circuit divided by time. And I might, but the flux, the flux is always equal through here and through there. So the flux through this loop is equal to the flux through that loop, and so the change in flux will be equal as a function of time as well. So there we go. Now, I want to actually find the ratio of the primary voltage to the secondary voltage. If I say that primary voltage divided by secondary voltage, I'm going to plug all this stuff in, I get negative N times primary delta phi primary over delta T, all that divided by negative N secondary divided by phi secondary over delta T. But these two are equal, so they can cancel out. Delta T in the denominator of the numerator and delta T in the denominator of the denominator also cancel out. The minus signs cancel out, giving me a plus sign. And I find this beautiful equation that the voltage ratio depends on the ratio of the number of turns. So the side that has more turns will have a greater voltage, assuming that the flux through each side is the same. Yes, and that makes sense because this is more sensitive to changes in flux. And this is less sensitive to changes in flux. So if I put a 2-volt supply over here, then I'm going to get out only 1 volt. Oh. Or I could make this side the primary and make this side the secondary. I could put 1 volt in over here and get out 2 volts. So it depends on the ratio of the number of wires wrapping around. Pretty handy. Now this is a way for me to change voltage. What if I used, let me just sketch one out for you. I don't want this to get confusing. I'm going to give you a green core. I'm going to give you a green core, and we'll go around here just 4 times. 2, 3, 4. All right, and then on the other side, I'm going to go around 40 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Great. Over here, I'm going to have the voltage of the secondary side. I can measure across this resistor, which is going to be my load. And I've got the voltage of my source put out by an AC generator. It's supposed to be a picture of a wave because that's what that voltage looks like. And this is the voltage of the primary circuit. Now I could argue that the voltage of the secondary circuit is the voltage of the primary circuit times, oh, what did we have? We had this ratio over here. Let me see if I can make some sense out of this thing. I need to make some sense out of that. Basically, I'm solving it for voltage secondary. So I think it's going to be the number of, this is the number of turns primary, and this is the number of turns secondary. And if I'm solving it for voltage secondary, it's going to be the number of turns in the secondary circuit divided by the number of turns in the primary circuit. Which in this case, well, I think that I'd plugged in that this is voltage primary divided by, or multiplied by 40 divided by 4, which is 10 times, in this case, the voltage of the primary circuit. So I've increased the voltage. That's awesome. And in fact, you see these transformers all over the place at a power generation station. They've got big transformers, and the wires, if I'm thinking about telephone poles like this, and I've got another telephone pole over here, these wires are incredibly high voltage. So if you see a balloon and you want to go up and get it, don't. Just don't go up there because it's actually really, really dangerous. They're very high voltage. Voltage is high, but before it goes up to somebody's house, like let's say your mom and dad live over here in a tiny little house with just one door and no windows, then there's going to be a, well, all 3 of these will join together with a little panel, and usually there'll be a little transformer right here. There'll be a transformer maybe here, and it looks like a cylinder. It's sometimes gray in the United States, hanging off the pole, and it feeds this wire over here, and those guys go whoop, over to your house. It's usually 3 wires all twisted together. All right, that probably depends on where you live. But you're going to get some energy delivered to their house because this transformer is lowering it down to only 120 volts in the United States. And these guys out here might be 1,000 volts or 2,000 volts. And in fact, the ones that go from city to city, the really big power lines, might be hundreds of thousands of volts. And we'll talk about why you'd want to do that in just a moment. But first, agree that I can raise the voltage, which means more pushing, right? That's awesome, more pushing. But it comes at the expense of what? Greater output voltage is possible. But who's buying, right? Why can that happen? It seems like you're getting more energy. And you know that voltage is energy per charge, so I'm thinking maybe you don't have as many charges. Let's see if we can justify that. I want to argue that power in must be equal to power out. And in fact, that's sort of even assuming that efficiency is equal to 1. That would mean that efficiency, well, you know, efficiency, if you work out, you win, right? And if I divide both of these by time, I would find power out over power in. If you pout, then you pin. That's sort of a wrestling phrase. But this is input power, so it's going to be power in time, or sorry, current in times voltage in. And output power has to be current out times voltage out. And in the language of a transformer, we're talking about current of the primary times voltage of the primary must be equal to current of the secondary times voltage of the secondary circuit. So if I rearrange these for voltage, what if I rearrange these for voltage primary over voltage secondary? Check that out. Then I'm going to get current secondary divided by voltage. Whoa. I don't know how that happened. Sorry, current, wow, let's just back the heck up. This is current secondary divided by current primary. So I gain voltage based on the number of turns. Remember what this was? Voltage primary over voltage secondary. This is the number of turns primary divided by the number of turns secondary. So this is all a true relationship, and it says that voltage might increase, but you pay for it because the current decreases. Now here's the beautiful thing. You know that resistive heating is, well, we call it Joule heating. Joule heating's like I squared times R. And if you've got some power lines up here, and those power lines have a fixed resistance, maybe you decided you're Ameren and you decided the best way to build your power line. They have a fixed resistance here. Do you want a high voltage up here and therefore a small current? Or do you want a high current up here and therefore a small voltage? Here's the problem. A really high voltage would be very inconvenient. You couldn't lay your lines on the ground because if some kid touches them, that kid would die. And that's not okay. So if you're going to have the bother of having extremely high voltages, like the voltage of many cross-country supply lines is like 750,000 volts. This is extremely dangerous, so it's got to be way up high in the sky or buried well beneath the ground, and burying it is even more expensive than just hanging up in the sky. So the advantage of this, though, is that since your supply voltage is so high, your supply current can be very, very small, yet still supply the same power that's necessary. The higher the voltage goes, the lower the current goes, and if the lower the current goes, then the less energy you spend heating the countryside. Is that the point of electrical distribution systems, to heat the countryside? No! When I was a kid, there was this thing you would say to another kid when you greeted him. You'd say something like, Transformers, more than meets the eye. And so today we are going to talk about Transformers. And it's not that movie, but they're everywhere and they're taking over also. I will start by showing you that this is the battery charger for the very camera that you are seeing this video through. Whoa, this is kind of meta, right? This is, yeah, okay, cool. So it says right here, input 120 volts, 9 volts. All right, let's see what's inside of it. Inside of here we've got only a transformer and a little resistor right there. That's how you power your Nintendo Entertainment System. I mean, it's how I used to power my Nintendo Entertainment System. Here's one that's already broken. Oh wow, now it's really broken. Yeah, and you've got a transformer right here and a capacitor right here and some diodes. That's all you need to go from AC to DC and to change your voltage. It says it's 120 volts and it goes to 12 volts, like a factor of 10. That's pretty cool, and less voltage out than I put. And that's an interesting relationship. Maybe you're thinking about how those are related, but I want to see what's inside of this sucker. Inside of here, we've got we've got this thing, and this is a transformer. So we'll investigate how that works. We've also got some capacitors and some diodes, and we could talk about how all that goes together at a later time, but yeah, we don't need that anymore. And oh, here's a nice one from a Nintendo Entertainment System. You ever heard of those? They're kind of old. And it says input 120 volts and output, and a range of voltage outputs between 22.5 to 18 volts. So the voltage is going down right here. It's called a step down transformer when you do that. Got some other transformers here. Let's see, here's one. Yeah, here's a Radio Shack transformer, and it's got this plug at the end right here, and it was designed to power some small toy, probably. It says input 120 volts, 80 milliamps, and output 9 volts, 350 milliamps. Whoa! Okay, so I get more current out than I put in, and I get to 100 volts to 240 volts, huge range. It says 50 to 60 hertz, so something must be changing up and down. And the output is 4.2 volts DC, and it's 500 milliamps. So that's a very small current and a very small voltage output, but a much bigger voltage input. So something must be changing the voltage in here. So let's look at another one. I've got this one, where's one? Oh yeah, you might have a transformer for your laptop inside a block that looks like this. This one says that the input is, again, a huge range of voltage inputs.